part number 7, I will address what is actually going on in the neural processing. And this is also strongly related to the inner hair cells, which are, as I mentioned before, the sensors for the vibration. And we saw already on some example videos how the hair cells are moved on the basilar membrane, and their hairs are moving due to the vibration. And here we see, before we go back into more details again, we see the total cross-section of the cochlea, just again, schematically, of course. And there we see the basilar membrane, which mainly divides the cochlea into the 2 parts, the upper and the lower part. The upper part, the most upper part is called scala vestibuli, and the lower part is called scala tympani. And this is more the mechanical separation by the basilar membrane. But we see here another membrane, which is called Reisner's membrane. And this membrane is has no direct mechanical effect, but it's more kind of an electrical effect, because there is one thing which is called stria vascularis, and this can generate potassium ions and emit potassium ions into this part, which is then closed from the other part, or separated from the other parts. In terms of the ions, they can't easily get out of this middle part, which is called then scala media. So there would be, in normal cases, some kind of potassium ion concentration here. And now, before we see what that means and what's the effect of that, we get again a closer look into the structure of the organ of Corti. We saw that also before, a bit more words are here, or names of different components here. Here we see the so-called tectorial membrane. We see the outer hair cells with their stereocilia, and here, of course, they would be in a row going into the depth direction. And here we have one inner hair cell, and there would be normally one row of inner hair cells here. And there we see the stereocilia. And we see that there are auditory nerve fibers getting close to the inner hair cell, but also there are some nerve fibers going towards the outer hair cells. And there are 2 types, or let's say the nerve fibers. These are all bundled in the auditory nerve, but these fibers are classified into 2 effects. One is called afferent, and the other one is called efferent. This comes from Latin. A lot of medical words are from Latin. Afferent means ad ferre, that means it carries something to somewhere. And efferent means ex ferre, means carrying away from. And this is actually what we see here, that we have both effects. The one fibers mainly carry information to the brain, which are mainly the ones coming from the inner hair cells, and the outer hair cells mainly have nerve fibers which are carrying information from the brain, so they can apparently be to some extent controlled in their activity by the brain, and only very limited part is also giving information towards the brain. So, but we'll come to that later. Yeah, and we see here that this part is all in the scala media, where we have this the potassium ions. And as I said before, the nerve fibers are bundled in the center of the spiral. That's why the inner hair cells are closer to the center. That's why they're called inner hair cells. And here on this side would be the center of the spiral. We see some other supporting cells and so on. That it's not that important for us, but we see that we have some kind of connections between the hair cell and the nerve fibers. And we would, I'm going to look closer into the details of those hair cells, and especially for the inner hair cells now. So, and here we see that we have multiple connections to nerve fibers, and A stands for afferent and E for efferent. So here you see it in a written form, so it's hopefully good enough. And also we see that here we have also some efferent and afferent fibers being connected to the outer hair cell. Okay, and as I said, afferent means it goes to the brain, and efferent because it's in relation to the brain. What is E? Efferent X, which goes away from the brain. And you see that there's more of those here, but also some here. And there's much closer connection of the nerve fibers which carry information to the brain at the inner hair cells. So, and here we see again the stereocilia, and the hair cells, they have kind of a body which is again filled, and we would look now into the details of the hair cells. And I start with the hairs themselves, the stereocilia, and we have a closer look at those. And actually they are not really hairs, but they are small tubes, what we call hairs or stereocilia. And if they are bent to one side, in this case to the left side, or in this graph, they are just closed, so nothing happens. But if they are moved to the other side, you can see that there are some connections here, and by their construction, there are some openings of those tubes. And once they are opened, the potassium ions can enter these channels, these tubes, and can enter the body of the hair cell if their hair cells are bent to this one direction. And you can imagine the more it's opened, the faster they can move to the inside. And because they have a positive potential, they would change the potential within the body of the hair cell. There we have the connection of vibration and electrical potential. So in steady state, there would be a negative potential in the inside, in the body of the hair cell. And so there's a negative potential. And if the channels are opened, then let's say, of course, the positively charged potassium ions would enter the body and lead to a depolarization. That means the potential would get closer to zero. I hope that's logical. And then there is some diffusion, and so they can be exchanged through the membrane of this hair cell. So once the channels are closed, the potential will get back to negative towards these minus 40 to 45 millivolts. And then if the cells are depolarized, that means if the potential gets closer to zero, then here are some some transmitters, neurotransmitters, which would be then emitted through the membrane at the bottom of the cell in this graph, and then would activate the neurons, the actual nerve fibers here. So that's basically the mechanism of how mechanical vibration is connected to neural activities. If the hairs are moving, they would move to back and forth, and if they're moving to this one side where the channels are opening, potential increases from the negative potential towards zero, and then this would start the neurons here would start firing action potentials. That's the name for this kind of pulse-like information, which is then sent to the brain. And once they are closed again, they would stop, and the potential would change. And now it's a matter of timing. How quickly do the potassium ions enter the body, and how quickly do they again diffuse? The diffusion works so that they would get out of the body again. So how long it takes for repolarization. So and that's important for the effects we will see in the next slide. You can imagine first, this is some kind of rectification effect we have, because if it's moving towards one side, the channels are opening, but if it's moving to the other side, they are slightly opened in the case of quiet, but only very slightly. So they would be still closed a bit further, but then nothing else would happen even if they would be moved further to the left, and in the previous graph at least, and then only the vibration in one direction is then having some impact on the potential of the hair cell. Then we have some kind of chemical or electrochemical processes going on, depending on how fast this diffusion works. We have kind of a low pass filtering characteristic, and that's what we can observe if we excite the basilar membrane with a certain frequency and measure the membrane voltage for these different stimuli. So if we have fairly low frequencies, like here it's one for 300 hertz, a 300 hertz tone, we have the vibration, so 300 times per second it moves to the right and then to the left again, and so on. And so we see here that this 300 hertz is still visible in the potential of the hair cell or the membrane voltage. At 500 hertz, we see that it's moving up and down. The voltage is moving up and down faster, of course. Still it's 700 hertz, and at 1 kilohertz, the vibration or this is quite strong. Probably this was close to the characteristic frequency, so that there is a strong variation. But we see also that already there's some constant increase of the potential. This is more visible than because here we see the potential in the steady state, in the quiet phase after the tone burst was switched off. And so here we still see there's some vibration going up and down, variation going up and down. And here it's more or less going up. So there is some kind of increase also of the average potential in that during the tone burst is on. And if the frequency is increased further, we see that there's more at 2 kilohertz. We see that there's more constant, like a DC component, which would correspond to the envelope of the sound rather than the actual vibration. But still there is quite some vibration visible. some part of the vibration, like of the actual frequency. But the higher the frequency gets, the less we see of this change of potentials going up and down during the caused by the vibration itself. But at high frequencies, we more or less see only the envelope of the vibration and not the individual periods anymore. So that is one important thing also for our pitch perception, perceived perception of frequencies, that we can imagine that for lower frequencies, we would still be able to detect some kind of periodicity in the potential, if that would be covered in the firing of the neurons, but we'll come to that later. So that is, we still have here the vibration itself is still visible, and at higher frequencies, it's no longer visible. Yeah.
How the inner hair cells get the potential back to the default?
Yeah, partly by this diffusion, that the ions can move through the membrane out, so then the potential would get more to the negative again. And yeah, maybe first summarize that, and then we'll get to a bit more to the further neural processing, and I will show you how models are built more on this electrochemical, trying to model this electrochemical process, and other models that are very much simpler, depending on what you want to model. So the hair cells, there are some kind of neurons, but not really neurons. They don't fire action potentials. They are also called spikes, what we'll also see later. But they have synaptic contacts to neurons, which are then the so-called spiral ganglion cells, because they are the ones which are in the auditory nerve, go through in the center of this spiral, where they are connected to the auditory nerve. And what can be generally said is that the depolarization of the hair cell, that means if the potential gets closer to zero, the firing rate of a spiral ganglion cell, which is connected to the corresponding hair cell, is increasing. So there's a mechanism of seeing this potential, what we saw on the previous slide, and the firing rate. So there's a connection of the two. And the axons, this is more or less the contacts. As an electrical engineer, I would say these are the contacts, and then the nerve fiber has some kind of cable and is connecting to the brain. And we see how example neuron looks like. So they are bundled in the auditory nerve, and then they are connected to the first stage in the brain, which processes signals from the auditory system, which is the so-called cochlear nucleus. So this is the part which is connected to the cochlea. That's why it got its name from. And this is just one example of a neuron. There are different neurons, kinds of neurons in the body, so I will show you that as well. But we have one neuron. In this case, this is a so-called multipolar neuron. This has one end where there's the so-called nucleus. This would be the sender side, I would say, again in engineering terms. And they can have multiple connections to other parts, like which could be hair cells, which are called dendrites. And if there is activity, some kind of electrical activity, then they could then generate an action potential, which is a pulse-like electrical potential, and this would then be carried via the so-called axon, which is the fiber which can have a, depending on where the information has to be transmitted, can have a certain length and also can have different structures. And then there would be terminals on the other side, which could then connect to other neurons, for example, where the information is then further processed. So it's not just a one-to-one connection, but we can have multiple connections on this side and also multiple connections. So the information could also be distributed to different other neurons, for example. And they can have kind of an insulation, but the main thing is that the information, this pulse-like information, would then be carried via these cells, so that in the end the pulse arrives at the other end. But this is not the only way neurons can look like. You can have unipolar, bipolar, multipolar, and so on. It depends on if there's more or less for sensors, or what's kind of their task, if they would also control some muscles and so on. Maybe people from medical engineering know much more about all that than I do. But just to let you know, but the ones which are connected, mainly transmitting information from the auditory system to the brain, are more of this kind. So they could be connected to multiple different hair cells, because they have multiple connections on one side, and could also be connected to different neurons in the cochlear nucleus. And so the sound can be, or the events, the auditory events, can be processed in different ways on both sides. Okay, here is a little bit of summary. The neurons can be classified once by the direction of the neural activity, if they are carrying the information to the brain. That's also called sensory, because they capture some information and carry it to the brain. Or if they are, then this is afferent again, and afferent is, they are also called motor cells from the brain, because they often, for example, control muscles. Another way to classify nerve fibers is by their structure. And in the auditory nerve, they're classified with two types. There's a type 1, which is mainly connected to the inner hair cells. They have a relatively large diameter and are bipolar and are myelinated. This is more or less kind of an insulation. And they allow a relatively fast signal conduction. So here the number shows 60 to 120 meters per second. So that sounds which are captured can be processed quite quickly without much delay. And the other type 2 is mainly, these type 2 neurons are mainly connected to the outer hair cells. They have a smaller diameter and are unipolar and unmyelinated. So they have a relatively slow signal conduction. So they are, and they're mainly also, so here I found different numbers. That's why I put a question mark here. So somewhat, but significantly lower or slower than the type 1 neurons. So this is actually the information of the audio signal itself, and this would be more kind of environmental or control information, which would not directly transmit the sound. And another way of classification is by their so-called spontaneous rate. the spontaneous rate is the number of spikes per second in quiet. That means if there's no sound. That means that there is some of the neurons do regularly, or not, of course not periodically, but with a certain rate generate spikes, even if there's no sound. And there are some neurons which have a relatively high spontaneous rate, but for say understanding the term high, we have to see how far it can go up. So they have a spontaneous rate of normally between 20 and 50 spikes per second. And in the auditory nerve of those afferent neurons, about 60% of the neurons are of high spontaneous rate. They have a relatively high, as the name says, high spontaneous rate, high rate when there's no sound. Then the firing rate would increase relatively quickly when there is some low-level sounds, but then they would already saturate at sound pressure levels which are clearly below 50 dB. But they would, let's say, right away in levels, let's say around 0 dB, they would already show some increase of their firing rates. Then there are other types of neurons which are then called with a medium spontaneous rate. This is a bit lower. And I think this is not a real classification, but this is just an approximate ranges are given here just to show that this can also vary quite strongly, but about 23% of the neurons in the auditory nerve are of the medium spontaneous rate, and they have generate not so many spikes in quiet, but then also the rate would not start increasing already at 0 dB, but just it would kick in, let's say, starting at 10 dB, 10 to 20 dB, and then at only levels above that would increase the firing rate significantly. But then they don't go to saturation as early as the first class. And then the third of those classes are the low spontaneous rate. They have less than 1 spike per second. And we have about 16% of those neurons. And there the firing rate only increases at levels above 20 or 30 dB. Of course, they don't have all exactly the same limit, but the range of where they start firing more or increasing their firing rate is in that range. And on the other hand, they don't have a saturation below 80 dB, so they would also not directly go into saturation, but would be quite significant change depending on the level and until up to 80 dB. And this can be shown more or less in graphs, as it's shown here. Here they use the letters A, B, and C for high, medium, and low spontaneous rate. Here, just one example. Here, this would start at 50 spikes per second, already at 0 dB SPL, and then the rate would increase until the level is somewhat around 20 dB in this case, and then it would not increase any further. And the next, the B, the medium spontaneous rate neuron, that would start a little bit above 10 dB SPL, and then it would increase, its firing rate would increase, and then here the saturation is not yet clearly visible in that graph, but it would then sometime at some levels here above, let's say, 40 dB or so, or 50 dB, then would go to saturation. And we see here that the low spontaneous rate, they have no significant activity low sound pressure levels, and then they start increasing their firing rate, and this could still increase even at levels above 8 dB SPL. And you can imagine that this, by this way, the neurons can cover jointly, because multiple neurons can be connected to each hair cell. As we saw before, there are multiple connections. They can cover the whole dynamic range, the whole hearing range in terms of sound pressure levels, that the high spontaneous rate neurons, they would cover the low level sounds, and then as the level increases, the others kick in and also produce some increase of firing rate. And so by this, the total firing rate covers the whole sound pressure level range. And this can be made combined. So here it shows you have an input sound level. This is a bit similar to the previous graph, a bit simplified, the saturations and so. But to show the ranges of sound pressure levels where the different neurons are relevant, you can say in the first range, which would be then the range here up to something like somewhat between 10 and 20 dB. The first high spontaneous rate neurons would be relevant with their firing rate. Then, of course, the total firing rate would be the sum of those, and we see here then the firing rate as how it would change. But this is not the firing rate in spikes per second. What we see here, this can go way higher, but the connection of level and the relative response is shown here. Here is again the spikes per second, and this is then connected to this graph. We see that there's kind of a nonlinear connection, but also that for higher levels, it's mainly the sensation is mainly generated by the low spontaneous rate fibers. And then regarding spikes, I talked about spikes all the time. This is one example spike or action potential. If we talk about neural activities, we have to know what that means. So if there would be a stimulus present, or let's say switched on at a certain point, there would be again some electrical processes going on in that neuron. And if the stimulus is strong enough, so there could be some failed initiations, but if then actually the stimulus activates a spike, then there would be a phase of depolarization. And if that depolarization goes above a certain threshold, then it will generate a full action potential, which looks like this pulse-like thing. And then there's kind of a negative polarization or voltage phase, or lower voltage phase. It's changing around about minus 70 millivolts, and then that would go back to a resting state. And what is important, that the spikes have a constant amplitude. That means the amplitude of the spikes does not convey information about the strength of the audio signal, but just the number of spikes. Because either there is a spike or there's no spike. So these failed initiations, they don't count, let's say. So actually either it has the full amplitude or there's no spike. Yeah.
Two questions, actually. Yeah. First question would be, because if you take a look at the time axis, did see that the whole depolarization, the repolarization, the refractory process takes about 4 milliseconds. Is this a typical number, 4 milliseconds? Is this like, can you say this is somehow connected to our time resolution capacity, or is this?
I found just this for explaining that, but actually the spike rates of individual neurons can go up to 1,000 spikes per second. So that must be shorter in this case. There must be some spikes which are able to increase in their firing rate higher. So, but
there has to be some upper limit, I guess.
So the let's say the upper limit is really about 1 kilohertz, but not 1,000 spikes per second. But also a lot of neurons have a lower limit. So that's, if you go back to maybe even to this graph, you see that most have a saturation somewhat below 300 spikes per second. But this doesn't, but since we have multiple neurons, they would not necessarily fire all at the same time. So the total firing rate can then, of course, get higher, even for the information which is coming generated by one hair cell, let's say.
And second question would be actually to the slide before. Why does the relative response increase more at 80 dB input sound level? And
actually, higher? I didn't find any comment about that in the literature.
Okay.
Sorry. I can check if I find some information, but I also wondered a little bit how that works. But yeah, maybe there would be still some neurons
because
kicking in.
If I understand it correctly, the beginning is pretty steep because of the addition of all the three
because we have many of those. We have 60% of those
exactly.
Neurons. Yeah.
Then it gets a little more flat
when they don't produce as increase their firing rate anymore, but those kick in. But there we have a lower percentage in the total, and even less of those.
But this would indicate or some there must be some for the low
So up to here, everything looks kind of.
There should be some kind of mechanism that they start firing faster with maybe input levels above 80 dB or something like that.
Or it could be that then they have more neighboring neurons also would be involved, because we know that this nonlinear behavior might then make since the width of the response is getting increasing, so that might make that at high levels might make the total number of spikes per second, which would be measured on the new auditory nerve, increase again. So this might be one reason, but I can check it up if I find that information. Yeah. So
speculation.
Yeah, it's kind of speculation. Okay. Any other questions? And here I want to repeat again. This is binary. I think I have it on a slide as well. This spike shape and amplitude is not depending on the input level of the sound. So here it is. The spikes is more or less a binary thing. Either there's a spike or not. And the maximum firing rates can for a short time go up to 1 kilohertz. That means 1,000 spikes per second. And permanently the limit is around 600 spikes per second. And since we have multiple fibers with different spontaneous rates, there is kind of a continuous pattern connecting the sound pressure level and this total spike rate. This is a bit of a summary of what we saw before. And some other things which might be interesting. First, again, coming back to the outer hair cells, we have about 12,000 outer hair cells. They're in the human auditory system up to 5 rows. And each of those outer hair cells has about 140 stereocilia. And each of the outer hair cells is contacted by about 6 efferent nerve fibers. It means which are coming from the brain, having some influence. Apparently, there must be some impact on the activity of the outer hair cells. Let's say one thing which I read might be that they are responsible, to some extent responsible for the so-called cocktail party effect, which means in a conversation or if we are in a noisy environment, we can focus on certain sound events. But it's not, I haven't found direct proofs of that. But some possible things would be that the brain can control where the outer hair cells amplify sounds and where not. And this could then lead to the fact that certain frequency regions where we maybe unconsciously, but we would focus on someone speaking and we want to understand that, that would focus then on the corresponding sounds and maybe give less emphasis on other frequency regions. So, but the fact is that there are about 6 efferent nerve fibers contacting every outer hair cell, but every of those nerve fibers does not only contact one outer hair cell, but about 10 in total, or 10 particularly. So in that region, that one nerve fiber coming, one information from one auditory nerve fiber could influence multiple outer hair cells. The inner hair cells, we have less of them. We have about 3,500 in one row, and each has about 40 stereocilia, so less than the outer hair cells, and each is contacted by up to 20 efferent nerve fibers. It means from this, the sensor, one hair cell could contact or would produce, could influence the firing rate of 20 nerve fibers. So there might be some connection of neighboring regions, but as we see here, we have 3,500. So if some neighboring inner hair cells are connected to that same nerve fiber, this would still be quite a high frequency resolution. But again, this could also be different, and the nerve fibers, they are not so the nerve fibers themselves can also contact different hair cells, but also these up to 20 nerve fibers can then also be processed in different neurons in the cochlear nucleus. So they could be analyzed in different ways. And I have some indications of what kind of cells are then processing these, let's say, signals generated here. And from this, if we measure neural activities, we can get some kind of patterns of neural activities depending on the sound pressure level and frequency and so on. And this led to some representations of neural activities, which would be then called a neurogram. But here we would first look into a spectrogram. This is what we know. In this case, it's not colored, but it's just grayscale. With high sound pressure levels have dark color, and low sound pressure levels have a light color. And here there was a focus put on one region of that spoken sentence. Joe took father's green shoe bench out, and the screen, the pitch goes somewhat up. You see that there's a component with a varying pitch here. And this is then again marked in the next graph, which shows not that as continuous as we do a spectral analysis, but if neural activities are measured at different characteristic frequencies, this is more or less a bit more sparsely sampled, but then the neural activity and the spike rates are measured at different neurons at the same time. Then we see here how the sound is represented in neural activities at different characteristic frequencies. And here we see that in this range, we see how this activity goes sequentially from this characteristic frequency to this characteristic frequency. So there's then the temporal spectral content represented by the neural activities. So this is the quite general thing, but there's another thing which is important for how the sound is further processed, and this one effect is called phase locking. And it means if we have a relatively low frequency tone, which is just a sinusoidal sound pressure variation or pressure variation, and if that is fed to the auditory system and the spike rates or spikes are measured on one nerve fiber, we can observe that the firing is always at the same phase position within the vibration. It doesn't occur at every period, but if a spike occurs, it's more or less at the same position within one period. I don't know if this is visible enough, but this is kind of a synchronization, and this is called phase locking. So the spikes are, for at least for relatively low frequencies, the spikes are in their position, temporal position, locked to a certain phase. That means it seems like this threshold of evoking an action potential is connected to the phase. You can imagine once the potential is increasing a certain threshold in the inner hair cell, then the spike would be evoked, and then it would be again the potential would go back towards the negative potential it has in the resting state, and then it starts increasing again, and so the threshold would be again reached at the same position, and that's why we get this kind of somewhat phase synchronous spikes. This was done by a simulation, but there's also some measurements which seem to be quite old from the equipment they were using, but still I want to show it to you. These are spontaneous activities of the nerve and also oralized. Now you see once the tone is on, there's kind of a regular pattern in each of the tone bursts. Now they're synchronized to the phase of the input sound. You see that maybe at the beginning there's some kind of the maximum of the maybe the potential is larger to the beginning. So these are some experiments which show that phase synchronization. Of course, it's a matter of probability, but the main activity is close to a fixed position within each period of the sound. And this can be done by, or the more experiments had been carried out, let's say. And this was here an experiment measured at a nerve fiber at characteristic frequency of 4 kilohertz. And this was done for different tones. You see here different frequencies. The first one is a 1 kilohertz tone. And we see the histogram, that means how many percent of the spikes were at a certain position within the phase of the stimulus. It goes from 0 to 2 pi. And over all periods, they were summed up, and the percentage was shown here. And we see here that there's a clear peak for the 1 kilohertz tone, that the spikes are, most of the spikes are in that range here. For 2 kilohertz, the peak is a bit weaker, but still a maximum, there's a clear maximum. 2.5 kilohertz, still quite significant, but the higher the frequency gets, and if you look at 4 kilohertz, there's almost no clear dependency on the phase. So the spikes are now more or less randomly distributed over the period, over the positions in the periods of this 4 kilohertz tone. And that corresponds to some extent with what I showed before about this potential of the outer hair cell membrane, because once this is more or less constant, then there would be, the firing rate would be also kind of continuous. Yeah, you have a question?
How do you measure the spike rates?
I don't know exactly how they measure that, actually.
Because I could also imagine, I think I understand what you just said, but I could also imagine that with, of course, with higher frequencies, it gets a lot harder to distinguish between the
individual spikes.
Yeah.
But it's a single nerve fiber. That's why you have the more or less kind of a maximum of the firing rate. But and then you measure just where they are. And I think that's not that complicated with, let's say, higher sampling frequencies, which you can use for the electrical signals. But of course, there might be measuring noise and so on. But I think that's somewhat in correspondence with the voltages measured of the membrane of the inner hair cells. If there's no more direct variation of the voltage, then it's quite less likely that the firing is still depending on this periodicity. If the periodicity is no more visible in the membrane voltage. Yeah, so this is the so-called phase locking, and for the next part, I would like to show some models for the hair cells before going then into the further neural processing. And first, you can model the hair cell to firing rate connection in a fairly simple way. And this was, for example, done by in the model by Frank Baumgarte, who wanted more or less to get a good connection of time and frequency resolution of the auditory system. And the cochlea was modeled quite close to physiology. But after that, there was a relatively simple model, just rectification. In this case, he did not use one-way rectification, but he just squared the input, which is some kind of rectification. You get only positive output. and but you use two halves of the period, and the calculation of the square is kind of a calculation of the intensity included already. And after this, rectification and squaring is kind of a first order low pass filter by an RC component. And this would have this low pass characteristic that if you have low frequencies of a sinusoidal stimulation, this would still go up and go down again. So you would still see some part of the periodicity in the output, but not anymore for higher frequencies. Other models are much closer to and analyzed much more what's actually going on. The first part I explained already. The input is more or less the stereocilia displacement or the velocity of the basilar membrane. That's what they are connected to each other. Then we have this mechanism of the potassium ion entering and diffusion process. And what happens then further, I didn't show you before, is that there are neurotransmitters in the bottom of the hair cell, and they are then released when there's a depolarization. So they enter this kind of cleft, where then on the other side here, this would be the dendrite of the auditory nerve fiber. And so there would be neurotransmitters emitted from the hair cell, and when they reach this connection of the auditory nerve fiber, they could then, or if there are enough of them, they would then generate a spike or an action potential. So, and these are calcium ions, and so, and these neurotransmitters would then, of course, get out of the hair cell. They can be taken back into the cell. Some of them can be lost. Some can be, let's say, taken back into the hair cell, and some can be released from a transmitter factory. That's what it's called. And so there's some kind of dynamic process which is a bit complicated. So basically the potential here controls what happens in the lower part of the hair cell. And so this we have some time constants for the transmitter factory emitting, the rate of emitting the transmitters, the rate how much they enter the cleft, and how fast they can be taken back. And this is in one hair cell model incorporated. There is this is a block diagram for this model. So there would be a factory which always has some transmitters, and there is a certain rate by which they would be emitted from the factory and enter the free transmitter pool. So that would be more or less the actual neurotransmitters which can be emitted from the hair cell. And this would be then how many are leaving the hair cell to the cleft. This would be a constant Q, factor Q, multiplied or a value Q multiplied with a K, and K is actually the connection to the potential via the potassium ion concentration and so on. So this is a nonlinear function depending on the basilar membrane displacement. So, and here you see the kind of rectification. So there is some small offset, but if this S of t plus a is larger than 0, there would be some, this k would be larger than 0 as well, and else you would get this nonlinear function out. So, and this k controls then the amount of neurotransmitters being emitted to the cleft. And then we have in the cleft, there would be C is more or less representing the number of neurotransmitters in the cleft. Then a part of them is lost with a factor of L. The more there are, the more get lost, let's say, but the factor of the lost one, the ratio is L, and the others, there's a factor R for the reuptake, and then they come to the so-called reprocessing store W, and then with a rate of X times the amount being in the reprocessing store, they enter the free transmitter pool, and the others are added by, and the value Q is the amount of transmitters in this pool, and the more the difference between the one in the factory and the let's say filling grade of the free transmitter pool, the larger the difference, the more come in, and there's the factor Y is this the ratio of how fast more or less they get in. And yeah, let's say K times Q is also what the more are in the pool, the more can go to the cleft. So this would be, if this would be a steady state, this would be then kind of exponential changes until a steady state is reached. And we have some these factors L, R, K, and here X and Y. These are factors determining time constants, how fast the flow goes, and that means how fast there are changes. So this dynamic process changes. And first we can visualize this function. So this would be the K depending on the this basilar membrane displacement, S of t. We see the rectification, but also we see some nonlinearity here. And then the next stage is then the processing, again as an electrical circuit, where this store is always a kind of capacitor which can be filled by a current source. And so we have the capacitor for the free transmitter pool, Q, and this would be the factory. Yeah, and there could be some current going in, and then the maximum could be the same. The voltage here, if that's the same as the voltage here, there would be no more current coming from here. But then there would be something going out here to the cleft, and this is depending on the on this factor K. And then this current flowing to the cleft is in the current model is a current source here, which then would fill the cleft, and then here we see the loss and the reuptake. And the reprocessing store gets then the transmitters which go here. They are then used as a current source to fill the reprocessing store in this capacitor, and then this would be then again from the reprocessor store. This would then be the current which goes in the current here would then be added to the free transmitter pool here. So these dynamic processes are then modeling the dynamics of this for let's say getting very let's say trying to model the temporal behavior of the of hair cells in what they generate and then how they are related to the firing rate, because then the neurotransmitters in the cleft, the number is directly then connected to the firing rate. So in this kind of not simple, but electrical circuit diagram with capacitors and resistors. Again, I must say that these blocks are resistors. In countries outside of Germany, many countries use a different symbol for resistor. So, and this is a variable resistor here. But that shows how these models were set up and then implemented with wave-neutral filters. And what you get out by that is a kind of dynamical behavior. And you can imagine that there is something that is not just like the number of transmitters in the cleft is proportional to the displacement of the basilar membrane, but it's more complex. And so they measured on one fiber the rate and intensity functions. That means if the sound intensity of a tone burst is measured, what kind of firing rate is generated in spikes per second. And here they use relative intensity, so it's not directly normalized, but in dB, so you have a certain range of sound pressure levels, and you can measure the firing rate immediately after the onset of a tone burst, or after the tone was already switched on for a while. So this would be then the steady state, would be measured quite a bit after the tone was switched on. There, interestingly, you don't see much level dependency. With this measurement they had here, but immediately after the onset, or this was 300 milliseconds after the onset, and this was quite immediately after the onset, just 1 millisecond or 2.5 milliseconds. You see that there's a clear dependency of the neural activity, which is measured and which is modeled by this model. So those two effects are captured relatively well. So this would be for tone onsets, and other experiments show then that you have a adaptation of the firing rate to tone bursts, temporal behavior. So at the beginning, at the onset, there's a quite strong overshoot, or let's say not overshoot, but strong peak of firing rate, and then it decays to with this effect. And once the tone is switched off, you have also for a short time you have almost no neural activity, and then it goes back to the spontaneous rate, let's say. And again, there's quite a good similarity of both temporal behaviors. If you have this direct onset and offset of tones, but also there are things which are not so well captured. That means the other experiments showed the reaction to a level increase or decrease. That means that it's not from 0 to on, but just a certain increase in level by plus 6 dB or minus 6 dB, a decrease of the level by minus 6 dB. And if you measure the impact of that for different times, like 10 milliseconds after this level change, or 1 millisecond after the level change, here you see there's a much stronger impact when you are close to the onset. this was for different durations. So this is the level difference between the level change and the measurement. And you see here that the model produces quite a strong reaction on the level increase or decrease shortly after the level increase was or the level change was moved in time, so that it was shortly after the onset or long or later. And then the question is how long this level change is. And so you see here that there's a strong variation, and here there's a weaker variation if you are not that close to the onset. And the experimental results are not shown here, but they would be for the cases A, B, and D. There would be no significant dependency on the delay. That means they would have more or less flat curves. So here the model is not in such a good correspondence to the actual experimental result data. But nevertheless, this model, this MEDIS inner hair cell model, is used in some models of the human auditory, models for the human auditory system. So it's quite frequently used. So time is over. I have still a bit, but maybe then we can restart here at this point next time. Okay. Any immediate question? Yeah.
I was thinking about this phase locking mechanism, and I don't know if you mentioned it, but what do we get from that? Is this just something we saw, or do we get anything from that?
I come back to that later, yeah, but we have something from it, and I can already say it, but this will be repeated later, that our pitch perception is also frequency dependent. For higher frequencies, it's mainly the location on the basilar membrane. But for lower frequencies, you can imagine if you have a harmonic tone of, let's say, 50 Hertz, you have many harmonics which are quite close to each other. It would be fairly difficult to actually find out the pitch from the shape of the excitation of the basilar membrane. It would be there would be something going on everywhere, more or less. But once you have this periodic signal, and if you have the phase locking, we can then perceive the pitch by the time, let's say by the periodicity of the neural activities, rather than by the distribution over the basilar membrane. So this is there's one thing is called temporal pitch, where we evaluate the temporal structure of the neural activity. And the other one is called place pitch, where we evaluate the position of the maxima of the vibration of the basilar membrane, or the firing rate of the corresponding neurons associated to those places. Yeah. Yeah.
Is phase locking connected to spatial hearing?
Also, to some extent, for the lower frequencies. For lower frequencies, it's more phase variations. And as I mentioned at the beginning in spatial hearing, so, but for higher frequencies, there would be no more phase locking. So small phase differences would not matter anymore, but they would be anyway multiple periods. So there would be also it would not be easy to analyze some phase differences. So there's more time shifts. And for higher frequencies, these time shifts are more evaluated in the envelope of the signal rather than in the fine structure of the signal. So these effects are quite important for spatial hearing. Let's say for the binaural. The other thing is the pinna shape and things like that, but for binaural hearing, yes. Yeah, thanks for your questions. Yeah, one more here.
We on the slide before, or 2 slides before, I don't know. Yeah, let's take this one.
This one?
This one, yeah. Theoretically, if the firing rate would increase let's say, to the same amount, but for a longer time, would we hear better?
Hearing better, you mean we
Because
might be more sensitive, but but on the other hand, let's say with lower frequencies, we have more this the connection of the periodicity of the signal with the firing rate. So this would be more likely for a higher frequency tone, where it was measured here, where it would go more to a continuous firing rate after the onset of this tone burst. So depends on the frequency, and so this is only part of the picture what we see here.
Because I was in the beginning, I was thinking of the one slide for that. Because you mentioned the
steady state,
the cocktail party earlier. And I was thinking about the background noise of the cocktail party could also be the steady state, because this is something that doesn't change. And then if somebody starts to speak, maybe I don't know if this somehow
this might help to some extent. Also, let's say if there are really sudden sounds, we normally might have to react quickly. If it's kind of danger, then this would have a strong impact anyway. And with the cocktail party effect, it might help, but on the other hand, also, let's say, background sounds might have, like if you're in a restaurant, you get also noise from plates and all kind of let's say transition sounds and kind of percussive like sounds. But let's say speech is more in a range of pitch where we might have more of this effect, which is level dependent.